The next reaction I'm going to talk about is epoxidation of alkenes. Epoxidation is a reaction which derives its name from a class of compounds known as epoxides. Epoxides are compounds which have a three-membered ring with oxygen. So epoxidation is a reaction that converts an alkene into an epoxide. And these epoxides are useful compounds because they have oxygen, which means that they can be converted into other materials which have oxygen, such as alcohols or ketones, which are all very valuable compounds. In addition, it also has oxygen in a three-membered ring, which means that this ring is strained, and so all of these reactions that result in opening of three-membered ring, giving in production of some useful materials, are very facile because of the release ring strain. So it's not surprising that epoxides are hugely important for industrial commodities. They're produced on a very large scale, and ethylene oxide, which is basically epoxide of ethylene, is the most common one. So let's see how we make them in lab. We start with an alkene, and we react an alkene with this unusual looking compound which is known as peroxy acid. This is basically a carboxylic acid which has one extra oxygen and is able to transfer that oxygen onto an alkene to give us an epoxide and transform itself into just a normal carboxylic acid. Various peroxycarboxylic acids can be used. This will be peroxyacetic acid, which works very reasonably. This will be peroxybenzoic acid. And this finally will be metachloroperoxybenzoic acid, also known as MCPBA, which is the one that is used most frequently purely because it's crystalline, so it's very convenient to handle in lab. In terms of mechanism, the mechanism is actually very well understood and allows us to rationalize a lot of observations in this case. And the first thing that happens is the nucleophilic attack of the double bond on the oxygen, which then leads to transfer of this bond over here, capture of hydrogen by this double bond, and finally transfer over here to give us a transfer of one oxygen onto the alkene to give us the epoxide and the formation of carboxylic acid over here. This mechanism, you see a lot of things occur in the same step, and such mechanisms are known as concerted. Those things occur in concert and are actually very useful because they allow us again to have very predictable reactions. So the stereochemical outcome of this reaction is completely easy to understand because we basically have a syn addition of oxygen, so cis alkene gives us a cis epoxide. So this is how we make epoxides. Let's see what they're good for. So what we're starting to kind of see is a pattern with bromonium ions and epoxides now, that we go from an alkene to a three-membered ring, be it a bromonium ion or epoxide or something else, which is then opened to give us our final products. So if we have this cyclohexene, then using MCPBA, we can convert it into cyclohexene oxide. And this now can be protonated by acid to give us a protonated epoxide. Now this OH is a very good leaving group, and it can be easily opened again through a backside attack of, say, water to give us OH here and OH2 plus here, which then can lose a proton, to give us finally the transdiol. The trans geometry is a direct consequence of the backside attack that occurs. And this will be acid catalyzed epoxide open. It's pretty easy to see why we need acid catalysis here, because we basically need to convert our epoxide oxygen to a better leaving group, and then that will allow its opening with relatively weak nucleophiles such as water. But even though oxygen itself is not a very good leaving group normally, in the case of epoxides we can get away with much more because of the ring strength. So even without any protonation we can have a good nucleophile such as this thiol attack here, and because the reaction occurs on a three-membered ring and a lot of ring strain is released, this is actually an okay leaving group. And so now we can get this system, which is then protonated to give us our final product. Again, the geometry has to be trans, simply by virtue of stereochemistry of backside attack, but in this case, this will be acid which will occur without a catalyst, and it's a nucleophilic opening of box. Even though this is a little unusual case of SN2 reaction, the same rules apply. So if we have two sides which are of different steric bulk, the opening will occur on the more accessible side for the nucleophile, while in the case of acid catalysis, it will occur on the more hindered side because of the stability of the corresponding catalyst. And these reactions are obviously very useful because now we can introduce trans substitutions. We can get anti-addition of two different things with perfect control, and one of which is oxygen. But what if we want to do a cis addition, which is also needed in many cases? Well, for that, the epoxide opening will not quite work, and so we'll see in the next subtopic how we can introduce two hydroxy group in a cis orientation onto alkene.